Hi there. In this video, I'm going to teach you a little bit about implicit differentiation. So before I do a couple of examples, I'll just remind you a bit of what the chain rule is, and then we'll talk about how that chain rule applies to implicit differentiation. So if you had a complicated function like, well, it's not really super complicated, but if you had a complicated function that was 2x plus 7 to the fourth power, and you wanted to take the derivative of that, the chain rule says that you can treat it like it's a power, this to the fourth, so you're going to bring the 4 down, keep the bracket the same, so that was 2x plus 7, reduce the power to 3, so it looks like power rule, except in chain rule, you then had to multiply by the derivative of this embedded function, this function that's inside of the other one. It's really a composition of functions. So the interior function, you would take the derivative of 2x plus 7 and get a 2. So you could rewrite that as 8 bracket 2x plus 7 cubed. Now, this has always been the case. We just never really thought about it. So when we asked you in early derivatives to take the derivative of x to the 7th, you just wrote that y prime was equal to 7x to the 6. You didn't think about treating that as a bracket x to the 7, but it really is. So if you thought of it as the bracket and used chain rule on even this simple one, you would get 7x to the 6 times the derivative of what's in that bracket, which is x prime. But x prime is just 1. The derivative of x is 1. So when we apply that concept right there to a equation that has a y in it, then if you were taking the derivative of y squared, you would get 2y times the derivative of what's in the bracket, which is y prime. And you need to write the y prime down. The derivative of y to the 7th is 7y to the 6th, y prime, or dy by dx, if you'd like to use that notation. So implicit differentiation, you get these y primes that show up throughout your equations, but it's really a consequence of chain rule that's appearing in a question. So let's see what it looks like in action. So for my students, this is from page 113, number 7c. And you've got an equation that's given to you, and it's got y's and x's all over the place. So we can use implicit differentiation if we are just too lazy to solve for y, or if we cannot solve for y. So in this case, getting y isolated and by itself is going to be difficult. So to get its derivative, dy by dx, which is just y prime, trying to solve for y prime, we're going to have to take the derivative of the left and the derivative of the right, and then see if we can work some magic. All right, so switching colors, we're going to get, I look at this as two functions, 2x squared and y squared. The first function I will call f, and the second I will call g. So I will use our product rule that says f prime g plus fg prime. That's how you get the derivative of a product of two things being multiplied, or being taken the derivative of. So f prime, the derivative of 2x squared is 4x to the 1. And then you write g by itself, which is just y squared, plus f, which is 2x squared, and g prime is 2y, y prime. That is the thing that most people miss when they do these questions. They think the derivative of y squared is 2y. No, we're taking the x derivative here. So when you take the derivative of y squared, you get 2y, y prime. That's what makes this question different. If you're getting the answers wrong, that's probably why. Okay, so we've done the derivative of this side. I will now equals and do the derivative of the other side. The derivative of x cubed is 3x squared x prime, which is just 1. And the derivative of y cubed is 3y squared y prime. Now all of a sudden we have a y prime in two spots of this equation. So if I want to get those in one spot of that equation, I'm going to take them both to the left, and then I'm going to common factor that y prime out. So this term is going to head over there to the left. In order to common factor it, I'm going to need to get this term out of here. So it's going to go over to the right. And so after we rearrange things, this guy stays the same. So that's 4x squared y. And then y prime. Okay, that's this term right here. 4x squared y prime. Then we subtract 3y squared y prime, because he came over from the right. The 3x squared is left on this side. And we subtract the 4x y squared. Well, we're close to the end now. The whole point of bringing these two y primes over was so that we could take those out as a common factor. Meaning I could take that out and get 4x squared y minus 3y squared by removing the y prime from each and writing it out front. That way, if we were to extend it back in, you would get the equation above. And on the right-hand side, you get 3x squared minus 4xy. And we're now ready to divide both sides by that term. So y prime is 3x squared minus 4xy over 4x squared y minus 3y squared. The only other thing I see to do, you could take, it doesn't get you anything, but you could take out a common factor, as leaving the common factor in there just feels dirty. So you take an x out and you get 3x minus 4y. And on the bottom, you take a y out and you get 4x minus 3y. Nothing else that really cancels, so you'd leave it that way. And that's your y prime. That is your derivative using implicit differentiation. Let's try a different example. Okay, so from number 8D on the same page for my students, except this question, you're going to find the second derivative. That means take the derivative once and then do it again. So we'll take the first derivative. You're going to take the derivative of x squared. You get 2x plus derivative of y squared, 2y, y prime. Derivative of 16 is 0. Pause for a second. Why is the derivative of 16 0? Well, 16 is 16y to the 0 because y to the 0 is 1. If you took the product rule there, or the power rule, excuse me, you'd bring the 0 down and get 16 times 0 times y to the minus 1, and of course that is 0. Or you just memorize that the derivative of a constant is 0, which is what lesser math teachers will tell you to do. All right, so common factor of 2, since it's equal to 0, you divide everything by 2, and it's gone, so you just get x plus y prime equals 0. Notice how that 2 just disappeared. And now we can solve for y prime quite easy. You get y prime equals negative x, so kill that, and y prime equals negative x over y. That's first derivative. So if you want second derivative, you just do it again. So take the derivative of y prime and you get 2 primes. And now taking the derivative of this function requires you to have the quotient rule because you've got two things being divided. And your quotient rule said if you're dividing two things, you do f prime g minus fg prime over g squared. Don't get mad at me. I didn't make the rule. I'm just applying it. So my f is going to be negative x. My g is going to be y. So f prime is negative 1. G is just y minus f, which is a negative x. And g prime is just y prime all over g squared, which is y squared. Well, we need to do a little bit of trickery here. So you're going to get negative y, and here you're going to get positive x y prime over y squared. But I know from just up here that y prime equals negative x over y. If y prime is negative x over y, then I think I'm going to plug that in right there. So if I do that, I'm going to erase the y prime and put in negative x over y. Now I've got x over 1 times negative x over y. So this guy here becomes negative x squared over y. I'll give you a second to see it, because now I'm about to erase it and rewrite it. So negative x squared over y goes right in here. So now I have that term. This was y over 1. And I would like to add those two fractions together, but I can't. So I'm going to, because they don't have a common denominator. So I'm going to multiply by y over y. That gets these two as a common denominator. This term now becomes negative y squared over y. Take a good look, because I'm about to erase it and rewrite it. So negative y squared over y is what that term becomes. Now, if you've got those two fractions with the same denominator, you can combine them. So you are going to rewrite that as negative y squared minus x squared all over y. That's how this top is going to be rewritten, this numerator, excuse me. So we'll erase that and put in negative y squared minus x squared over y, and that whole thing is over y squared. Well, we've learned a few times now that you can just get those two guys together. Y is because you would take y squared over 1 as a fraction, bring it up, invert it, and multiply, and so that becomes a y cubed. So now we've got negative y squared minus x squared over y to the 3rd power. Well, you look up the answer in the back of the book, it doesn't quite give it that way. Well, we could take a negative 1 exponent or a common factor out, and you get x squared and y squared over y cubed. You look up your answer in the back of the book, of course, and they don't give that either. They say negative 16 over y cubed. And you're wondering what's up with that? Well, if you remember that x squared plus y squared equals 16 from the original equation, and you come down here at the end and you see x squared plus y squared, why not make it equal 16? And you get negative 16 over y cubed. And that there is an elegant, beautiful little solution for y double prime. At this point, by the way, the 3rd and 4th derivatives get much, much easier because the x just disappeared. Alrighty, let's look at the next. That was a lot of great simplification there. It was good fun. All right, next question. I think the last one I'll do. We've got x cubed plus y cubed equals 9xy. So you've got this function, and the question says, tell me the equation of a tangent line to a curve at the point 2, 4. Meaning, if you plug x of 2 and y of 4 into this original equation, the left side will equal the right side. All right, but what they want is an equation of a tangent line. How do you get an equation of a tangent line? Well, we're going to use an equation of a line formula. Y minus y1 is equal to m on x minus x1. And we've already got the x and the y. The x is 2, and the y1 is, sorry, the x1 is 2, and the y1 is 4. So you've got part of your points right here already. Like, you're close to the whole answer. What do you need? You need m, which is the slope of the tangent line. And how do you get the slope of the tangent line? Well, you need to take the derivative of this function. So you take the derivative. When you take the derivative, it gives you the equation that tells you the slope at any point. So you take the derivative, you plug in, because at what point you're going to plug in x of 2. That will equal the slope, and you will plug the slope in. So step 1, find the derivative. Step 2, plug in x of 2. Step 3, that will be your slope. Insert it into that formula and get the equation of the line. There's our roadmap for this question. Okay, so step one, figure out the derivative. Well, that requires, wait for it, implicit differentiation. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared y prime. And the derivative of 9xy is a product rule. 9x times y, we saw the formula with f and g. So you get f prime, which is 9, g, which is y, plus f, which is 9x, and g prime, which is y prime. So, like the last question, y primes to the left, non-y primes to the right, and you will get 3y squared y prime minus 9x y prime equals 9y minus 3x squared. Let's common factor the y prime out of here, and you get 3y squared minus 9x equals 9y minus 3x squared. Divide both sides by that term. 9y minus 3x squared over 3y squared minus 9x. Looks like a lot of 9's and 3's there. I bet you something cancels. Let's common factor in the numerator a 3 out, which would leave 3y minus x squared. And in the denominator, we'll factor a 3 out, which will leave y squared minus 3x. The 3 is now gone, and here's our equation for the derivative y prime. Well, that's where some questions stop, but if you recall, this was just step one. Find the derivative. Step two was plug in the point x of 2, and the y was 4. Plug those points in. So that's step one done. Step two, plug in 2, 4 into your slope equation. So my y prime is equal to 3y, which is 4, minus x squared over y squared minus 3 times x. So in the numerator, you have 12 minus 4. In the denominator, you've got 16 minus 6, which gives you 8 over 10, which is exactly 4/5. Don't write it as a decimal, please. So step 3 is to plug it into your equation. Y minus y1 is m on x minus x1. So in so doing, you would have y minus 4 is 4/5 x minus 2. So we got a couple of different ways we can write this equation. One of the ways, some of your textbooks want you to write things in a format like y equals mx plus b, because it is way easier to graph if you do that. Other textbooks like you to write things like ax plus by plus c equals 0 as a standard form. Look, whichever way you want to do it's fine. You can change from one to the other using like a grade 8 math or something, so it's not that big a deal. Let's take this equation and write it one way and then the other. So, considering that we go with this method, I would write y minus 4 equals, put the 4/5 on everything, and you get 4/5 x minus 8/5. Take this 4 over, and you get 4/5 x minus 8/5 plus 4, which is 20/5. And you have y equals 4/5 x plus 12/5. Now, if you wanted to write it the other way instead, that's one answer. If you wanted to write it the other way, you'd multiply everything by 5. You'd get 5y equals 4x plus 12. And then you could take everything to that side and get 4x minus 5y plus 12 equals 0. They're both the same line, two different equations for it. Okay, so in your implicit differentiation, if you notice what was different, to summarize everything up, you were getting y primes in the middle of your derivatives. That's really all you're adding, and it's just another opportunity for your teacher to give you harder and harder functions to take the derivative of. Hope that this was instructive for you and that you learned a lot.